Hello and welcome to the 10th and final lecture in this series on the topic of eco-modernism. I wanted to finish with what is definitely the most scientifically controversial topic in this series, and so far we've dealt with a lot of topics like nuclear power and genetic modification that are controversial in the public at large but not in the scientific community, and in fact the scientific community is always far less divided over those topics, being strongly in favour of both. However, within the scientific community, there is one topic that really does divide opinion, not only about whether it would work at all, but even if the risks are too great and it should never even be attempted. I'm talking about geoengineering, the act of altering our Earth's environment through direct intervention with the aim of returning our climate back to normal. And this is the big one. On the plus side, it's one approach that could potentially buy us a lot more time to reduce our CO2 emissions to zero without suffering the worst consequences of climate change. But on the other hand, it has the potential to go horribly wrong. After all, humans have a long history of trying to fix things with direct intervention and actually making everything worse. So let's start with that. You're probably wondering right now why I'm showing you a picture of a frog. Well, firstly, that's not a frog, it's a toad. In fact, it's a cane toad. And secondly, the reason why I'm showing you a cane toad is because they're a great example of human beings attempting to solve one giant problem with an extravagant solution and creating a much worse problem instead. Cane toads were first introduced into Australia in 1935 as a method of pest control. They are expected to contribute to an ongoing effort to control populations of the native grey-backed cane beetle, which looks a bit like this. And this is a pest which feeds on sugarcane and hence is a huge problem for the sugarcane industry. Cane toads eat these beetles, but they don't eat other more friendly species, so they were seen as the ideal solution. Within 2 years, over 60,000 toads had been released into the wild in northern Queensland. Since then, however, they've multiplied in number a little bit to over 200 million. Unfortunately, in these numbers, they stop being a help and they start being a hindrance. They can spread disease, and because they're also poisonous when consumed, they've contributed to the deaths of many native species and pets. There's currently no known way to stop the spread of this invasive species, and the destruction being caused is immense. Oh, and just as a final note, they don't actually appear to have reduced the population of cane beetles at all. This is the kind of story that we should have in mind when considering how we might use technological methods to fix the problem of climate change. In a sense, this is a lazy solution, one born of the lack of progress that we're currently making in reducing the CO2 emissions of our species through diplomacy and technology. The best solution to climate change is, after all, to stop burning stuff, to stop chopping down forests, to manage our soils correctly, to work to plant trees and encourage natural biodiversity. All those things will work, but they take time and, more importantly, money and political will. And if the climate crisis has taught us one thing, it's definitely that democratic political systems are terrible at fixing anything with a time horizon of longer than a few years. If we do fix the climate crisis naturally, and I use the word naturally in scare quotes of course, then it will certainly be too late to avoid a disastrous level of warming. So the question of geoengineering comes down to a balance between the likely harm that will happen if we don't reduce our CO2 output dramatically in the next few years, balanced against the risk of doing something potentially very dangerous indeed. Geoengineering will probably help fix the problem, but may have other side effects that we actually know about, and even some other side effects that we don't know about. And the main question to answer about whether we should consider this way of approaching the climate crisis is really, do we think we will fix the crisis in a less dramatic way within the available timescale? The answer to that appears, at least for now, to be a resounding no way. So I think geoengineering at least has to be on the table. It's a risk, of course, but at this stage we need to consider it as one of the options at our disposal. And maybe when it comes to the final decision, we'll decide not to take that risk. But at least we need to evaluate the option, work out what the risk is and what the potential benefits might be. My notes for this section, before I wrote it out in more detail, were 3 words. Currently, we're stuffed. Well, let's pad that out a bit though and see exactly what I mean by this. Countries have put a lot of climate plans on the table. The COP26 summit just ended included updates from a number of countries, pretty much all of which were wholly insufficient for solving the climate problem. If nobody changes their way, then our world will warm by between 2.3 to 2.9 degrees C by the end of the century. If they actually implement their inadequate pledges, then that pulls the numbers down slightly to around 2.2 to 2.7 degrees. That's bad. We're aiming for 1.5 degrees. Everyone signed on to that, but nobody is doing anywhere near enough to meet that goal. So 2.5 or 1.5 degrees. It doesn't sound like a huge difference, but it really is. 1.5 degrees is bad, don't misunderstand me, but it's not as bad as 2.5. This is the difference between a low probability of an ice-free Arctic and a virtual certainty. 2.5 degrees will significantly increase the number of severe heat waves, droughts and tropical storms, not by a few percent, but by more than double. The Intergovernmental Panel on Climate Change released a report in 2018 examining the difference between 1.5 and 2 degrees, a difference of just half a degree, and concluded that it will double the expected species loss, double the decline in marine fisheries, more than double the population exposed to severe heat waves, increase the sea level rise by 15%, and pretty much drive our coral reefs to extinction. Current pledges will make 2 degrees Celsius of warming look like nothing. But I think this isn't the entire picture. Government pledges are nowhere near enough, but most governments are nowhere near on track to meet those already insufficient pledges. This report in September 2021 by the Climate Action Tracker organisation doesn't pull any punches. Of all the countries surveyed, only one was doing enough to meet the Paris Climate Accord targets, the Gambia. Most of the world's largest polluters were classed as highly insufficient or critically insufficient. Words are cheap. Any government can commit to achieving a target by 2050 because they know they won't still personally be in power by that date, so they won't ever have to answer for their failures. So even though a lot of countries are working hard to reduce their CO2 emissions, none of them is really doing enough, and lots of countries are doing essentially nothing. We're installing solar power at an unprecedented rate. This report shows that we installed nearly 140 gigawatts of solar power globally in 2020 alone, but according to the IEA, the global energy demand is 170,000 terawatt hours per year and growing at 5%. So even if all that solar were in sunny climate like Spain, it would still only amount to roughly an additional 250 terawatt hours per year, or 0.14% of the total. In other words, global energy demand is growing 30 times faster than our solar capacity is growing. Sure, we can add wind power onto that, and hydro and tidal and wave energy and geothermal, and of course we should also add nuclear power too. But even with all of these, the unprecedented growth in low-carbon energy sources is not keeping up with even the extra demand every year, no matter making any impact against the legacy power demand. So yes, I stick with my initial assessment. Currently, we're stuffed. We need to at least consider a more dramatic solution, because it looks like the combined political will of humanity just isn't doing enough. The most obvious form of geoengineering, and one that perhaps doesn't even deserve the label itself, is direct carbon capture. I talked about this in an earlier lecture, but I want to distinguish direct air capture, which is the process of taking CO2 out of the air that's circulating around our planet, from the type of carbon capture and storage systems that have been proposed as an addition to existing fossil fuel plants. We investigated them before. They don't really work and they're too expensive. That's basically the summary of direct air capture too, as it happens. Though whereas investing money in carbon capture in traditional fossil fuel infrastructure seems like a horrible waste of money, postponing unnecessarily the inevitable death of the fossil fuel industry, investing money in direct air capture systems seems at least a bit more sensible. After all, even if we were to reduce our carbon dioxide output to net zero today, there would still be nearly twice the amount of CO2 in the atmosphere that our planet has had for the entire history of human civilization, up to the Industrial Revolution. That CO2 is still warming our planet, and we have to get rid of it somehow. Plants can do that to an extent, but only to an extent, and only at a certain rate. We want to speed up that rate as much as possible. We looked in detail at carbon capture in the 6th presentation in this series. In summary, there are several companies looking to build large-scale carbon capture systems. Perhaps the most famous is Geo-Engineering, a startup funded by Bill Gates, amongst others. Currently they have a pilot plant that sucks up 1 tonne of CO2 per day, which sounds like a lot until you realise that we emit roughly 35 billion tonnes per year, or 100 million tonnes per day. So even when carbon engineering do manage to build a full-size plant, and if they can get it to remove 1 million tonnes per year, which is their claim, then they will still need to build tens of thousands of them to negate our current global emissions. And that's not totally impossible, but it's clearly going to be very difficult. The second issue with carbon capture and storage is the storage part. The capture part is well and good, but if you don't have somewhere to store the billions and billions of tonnes of CO2 that you capture, then this scheme is never going to work. There are ways of doing this, either by pumping the CO2 down into porous rocks and then triggering mineralization, which basically turns the CO2 into rocks deep underground. Another way is to pump the CO2 back into the impermeable reservoirs where we pump the oil and gas out of. That also might work, but could clearly fail in a fairly spectacular way. Finally, the cost of this is not negligible. Carbon engineering reckons that at scale they can probably get the costs down to the $100 to $200 range, possibly dipping below $100 per tonne by 2030 once they get significant scale. However, there are still a huge number of question marks around whether this technology will be able to scale up successfully at all, and certainly whether it will scale up in time. The carbon cycle is well known, I hope, to most listeners, and one significant proportion of that is that carbon is sucked out of the air by plants. So planting trees is one way to reduce atmospheric CO2, but not all plants are the kind that you grow in your back garden. A vast amount of plant matter is of the form of phytoplankton. These are tiny microscopic plants that live in the oceans and drift on the ocean currents, photosynthesizing just like land plants do, taking in sunlight and CO2 and emitting oxygen. In fact, these tiny microscopic plants are responsible for creating roughly half of the carbon removal that happens around the world, and more than half of all the oxygen we breathe is produced by them. So how can we get more of these phytoplankton? Well, the answer is simple. Just like land plants, we need to provide them with nutrients. One of the main nutrients that they require, and which the oceans lack, is iron. Hence there is a theory that states that seeding parts of the ocean with huge amounts of powdered iron could stimulate the growth of large amounts of phytoplankton, and then hence sequester a vast amount of extra CO2. How plausible is this scenario? Well, as with most geoengineering solutions, there's a huge debate about whether iron sequestration is safe, and whether it even works. Several experiments have proved that excess iron can indeed produce blooms of phytoplankton, but there's debate around how much excess CO2 is actually removed from the atmosphere by this process. It's also worth pointing out that not all phytoplankton are benign. Some of them are toxic and can cause significant damage to fisheries and even human health. Ultimately, this is an intervention that could have huge and unpredictable effects to our oceans. Several studies have been undertaken and risks can be mitigated, but they're definitely not fully understood. There are always unknown unknowns, and playing with the root of the most important food chain on Earth is probably not a wise idea, until we're absolutely certain that we know what we're doing. So I think the answer here is further research is needed, but cautiously. Global warming happens because solar radiation strikes the Earth and is prevented from leaving by a blanket of greenhouse gases in the atmosphere. Most efforts we've looked at so far in this series focus on how we can remove that blanket, largely composed of CO2 and methane, and hence allow the excess heat to escape back into space. But another approach would be to stop the solar radiation from reaching the Earth's surface in the first place. This is Mount Tambora, a volcano in modern-day Indonesia. In 1815 it erupted violently in possibly the largest volcanic eruption in recorded history. Approximately 200 cubic kilometres of volcanic ash and soot were thrown into the atmosphere, which blanketed the entire globe for several years. The result of this, apart from the obvious local devastation, was a global reduction in temperatures of approximately half a degree Celsius the following year, making 1816 the so-called year without a summer. One significant contributor to this was a staggering amount of sulfur dioxide, SO2, ejected into the atmosphere, which blocks incoming solar radiation. It stops the heat from the sun reaching the Earth at all. So one suggestion is that we could do this ourselves, perhaps not on such a grand scale, but maybe to a smaller degree over the course of several decades. There is little doubt that this would work, but there's also little doubt that it would be a very drastic measure with drastic side effects. Sulfur dioxide is a primary contributor to acid rain, for example, and it also impacts the ozone layer. Excess levels of SO2 are bad for human beings, bad for plants, and generally bad for the Earth in general. This 2018 paper in Nature Climate Change examines the potential impact of using sulfur dioxide to slow down climate change, focusing on whether it would be safe to halve the warming caused by our CO2 emissions using this technique. It concludes that it might be safe and that the technique should definitely be studied further, but that there are clearly dangers. This is a drastic solution to a drastic problem. Of course, one other potential way to stop solar radiation from reaching the Earth is just to put a huge mirror up in space between the Earth and the Sun to block some of the light. This may seem attractive at first, as it obviously doesn't involve inserting huge volumes of acidic chemicals into our atmosphere, but unfortunately it's not a plausible solution, as a little bit of common sense will show. If you want to reduce the Sun's incoming radiation by 1%, then you'll need a mirror that roughly covers 1% of the Earth. Let's ignore the location that you place this at. It's not going to be in low Earth orbit, but if we assume it is, then it maximises the plausibility of this process. And as you'll see, it's still impossible. The Earth's surface, as seen from the Sun, is a disk of roughly 130 million square kilometres. 1% of that is, let's say, approximately 1 million square kilometres. That's an awful big mirror. So let's say we build a lot of smaller mirrors and launch them one by one. You can make a very big mirror by unfurling a large sheet of an extremely thin reflective material, but of course what that describes is a solar sail. So if you place that in orbit, the Sun will push it away. So you also need a powerful engine to counteract the thrust you get from the solar radiation. Let's ignore that too, because I'm being generous. And let's be outrageous and say you can make a mirror 1 hectare in size on each satellite. That's a square of 100 meters on each side. How many such mirrors would you need to shade 1% of the Earth? Well, the answer is you'd need 100 million of them. If you wanted to launch all those mirrors before 2050, then you'd better get started pretty soon, as that would be approximately 9,000 launches per day. That's roughly one every 8 or 9 seconds for 30 years. Good luck with that. Everything we've said so far has really considered the technical plausibility of the proposals. Would they work? Are they actually possible? Are they too dangerous to risk? But there's another angle here, which is that geoengineering is scary, and scary things are generally unpopular with the general public. When a small group of researchers from Harvard University proposed a small-scale experiment to explore the possibility of launching aerosols into the atmosphere to combat global warming, they were met with fierce opposition from the locals. The town of Kiruna in Sweden was chosen as a site for the experiment, but the locals wanted no part in this first exploratory investigation, even vetoing the first launch planned, which was merely designed to take some measurements and not spray anything at all. There are two sides to this debate. As the head of the project, Frank Koch, said in an interview, the risk of not doing research on this outweighs the risk of doing this research. And for the preliminary research planned by this team, that's definitely the case. Regardless whether we'll ever decide to deploy geoengineering efforts on a large scale, we ought at least to explore them and see if they're going to work at all. And if they won't work, then there's no point even considering them. If they will work, then we can at least keep them in our back pocket for when they're needed and we have no other options. But convincing the public that large-scale science experiments are safe is not an easy task. The public fear things that they don't understand, like nuclear power or GMOs, both of which we've covered in depth in this presentation series. The opposition coming from the public in both these cases has greatly worsened the impact of humanity on our planet and on the climate. But is the use of geoengineering exactly equivalent to these other techniques? Geoengineering is new, it's untested, and it's always going to be a gamble. By the time it's our only option left, our only hope will be to deploy it at scale and rapidly, and that means almost by definition that we'll never be able to test it sufficiently. Should we test it in a small scale though? Well, that raises other questions, most notably whether or not we even need geoengineering at all. By researching this Deus Ex Machina, get out of jail free card that geoengineering provides, we're giving the public hope that they don't really need to do anything to reduce their carbon footprint, because once it gets bad enough we'll just pull out a magical techno fix for everything and we can all go back to living how we were. Maybe researching geoengineering at all is doing more harm than good for purely this one reason. In summary, the human species is doing nowhere near enough to combat the climate threat, and it seems unlikely that humanity will be able to prevent at least 2 degrees of warming, probably more like 2.5 degrees at the current rate of change. And 2.5 degrees is really, really bad. Geoengineering might be the only fix to that. But on the flip side, research into geoengineering gives us a safety net, and that might be a bad thing. As long as there's hope for a magical fix to climate change, the public may not want to take the risk as seriously. On balance, it seems insane to leave potential fixes off the table though. A plan, no matter how risky, is better than no plan. Because if you have a plan, you can at least decide whether to activate it or not. But if you have no plan, then you have no options. And if climate change starts to get into the range of 3 degrees or even hotter, then I think by that stage we'll have to admit that the way we've been pursuing has not worked, and we'll need a pretty serious alternative. Some of the methods I've discussed in this talk might just give us that, but we should be very cautious and start doing research now so we'll know what we might be able to do when the time comes. Geoengineering is like a worst-case insurance. You hope your house never burns down, but you always have house insurance just in case. And yes, when your house does burn down, there will probably be a huge excess to pay and you'll have lost a great deal, but at least you won't have lost everything. We need insurance for the worst case, and let's hope we stop setting fire to our house in the meantime. Thanks very much for listening to this series on eco-modernism. I hope you found it useful. If you haven't listened to the rest of the presentations in this series, then they're linked on the video now. Please watch this space for more educational videos. And until next time, thanks for watching.